Hello, thank you. Hello and welcome to my talk. It's going to be on non-malleable codes from two-source extractors. It's a joint work with Stefan Dziembowski, who's unfortunately not here, Tomasz, Kazana, and the first guy is me. Okay, the plan of the talk, there will be three distinct parts. The first part, I will introduce the non-malleable codes. I'll try to give some intuitions and two alternative definitions. Also, I'll cover related work in this part. In the second part, I will tell about our construction, but it's not really going to be only our construction. It's going to be some kind of path between the ideas. Some will be good, some will be bad. Hopefully, it will give you the idea why the construction looks like it looks. So the construction will be at the end of this path. And the third part will be on leakage feature. I decided to take it out and put it in a separate part because it's shared between some papers and it's like a general idea. So let's start with the definition of non-malleable codes. Imagine we've got a message M and we want to store it on some kind of device. So we encode it and put it in the memory of this device. But then comes the evil adversary and decides to tamper with the device. The adversary chooses any function h from a capital H family. For now, capital H is just a family of functions, any family. It's just the definition. What happens now, we decode the memory and we obtain M prime. We can also think of it as we got M prime, an adversary tampered with it with function h tilde. Now, the adversary might or might not have full control over function h tilde. Why? Because scheme enc is random. So if the capital H family of functions is small, then adversary might not have enough power to counter this randomness. So he will have some partial control over function h tilde, but not full control. And now the definition is as follows. Actually, there's a typo, but never mind. Scheme is non-malleable with respect to family capital H. If for h tilde, there should be h tilde instead of h. If h tilde can be represented as a combination, probabilistic combination of constant functions and identity function. What it means on intuitive level is, okay, what can adversary do? He can change M, he can leave M and not change it at all. That's identity function. Or if he wants to change something, he will obtain something completely independent of initial message M. That's the constant functions. So that's the idea of non-malleable codes. And the problem is this definition is not very handy. It's hard to deal with theorems with this definition. So we came up with alternative definition for a case where M is just one bit. So if we got one bit, I will denote the initial bit as B and the last bit as B prime. So the alternative definition is as follows. The scheme is epsilon non-malleable or simply non-malleable with respect to family H. If for every function in this family, the probability that we will flip the initial secret, so the B prime will be different than B, is less than half plus some negligible factor. The B is uniform at start. Okay, so hopefully this is clear. So we've got two definitions. This one is very handy in case of one-bit secret, much easier to use. So in case of general message, we can only preserve the message or we can change it, but then we lose any information about the initial message. In case of one bit, we cannot flip the secret. This definition is completely equivalent to the general one in case of one bit. So there is that family H here and here. I didn't mention what's the capital H in our case. We're interested in split state model. What's a split state? It's a model where we encode the message in two parts, L and R, left and right. And what happens now, adversary can choose two manipulation functions, F and G, and he has to apply them separately to L and R. So for us, capital H is the family of functions which manipulate first half independent of manipulating the second half of the code word. So this is the capital H for us, and we're interested in creating the code which is non-malleable with respect to this family. Okay, related work. There are two papers I would like to talk about. First one is Non-malleable codes by Stefan Dziembowski, Krzysztof Pietrzak, and Daniel Weeks. What they do, they show the existence of the codes if the capital H family is small enough. It's actually not very small, but small enough. They do it via probabilistic argument, very cool argument with graph theorem. But the problem with this is the probabilistic argument does not really imply that there exists efficient code. It just implies that there exists any code, which is non-malleable. But they also give the explicit construction of non-malleable codes with respect to independent bit tampering family. What's the independent bit tampering? Sorry. Independent bit tampering is the family of manipulation where you apply manipulation to each coordinate separately. So you just tamper with each coordinate separately. The second paper is Tampering and Leakage Resilience in Split-State Model by Liu and Lizanskaya. They do something we're interested in. So they show the construction of non-malleable code in split-state model, though they show it with some additional assumptions. First of all, it's computationally secure, and second of all, they assume common reference string. They've got that bonus feature of resilience to leakage. I will cover it in the second last slide, I believe. Yeah. So what's our contribution? Well, we show the information theoretically secure non-malleable code for 1-bit messages in split-state model. Additionally, we got that feature of resilience to leakage. Okay, so the second part, construction. So first of all, the first idea is it has to be secret sharing. Why? Assume, I will show the example for 1-bit secret because it's the easiest way, and assume it's not secret sharing. Then what we do, we pick 3 vectors or 3 shares, L0, L1, and R, such that, you can see, L1 prime and R encodes 1, L0 and R encode 0. So what happens now? What's the manipulation functions? Well, G is constant function, always equal R prime. And what happens with F? It's not a secret sharing, so based on L, we can guess what's the secret. If we think that the secret is 1, then, well, we choose L0. If we think that the secret is 0, we choose L1. What happened now? Since it's not secret sharing, with high probability, we flip the secret. We flip the initial secret. If you remember the second definition, the code is non-malleable if you cannot flip the stored secret. So this one obviously is not non-malleable. And I think it gives you the idea why it has to be secret sharing. Well, it's not really a foolproof, but yeah. So we know it has to be a secret sharing. Is it enough to be just a secret sharing? And the answer is not. It's not enough. We require some additional features. Well, let's give a counterexample. This is the secret S and shares L and R. And the simple group operation is the sharing scheme. So what's the attack? Well, the attack is quite simple. We add 1 to L and leave R unchanged. What happens now? We obtain S plus 1. And if you remember the first definition, we said that adversary, which changes S to S plus 1 with function H tilde. If the code is non-malleable, the H tilde can be represented as the combination of constant functions and identity functions. Function S plus 1 clearly is not a combination of such functions, thus this is not non-malleable code. So we know that it has to be secret sharing, though the secret sharing is simply not enough. So what's the second idea? Well, let's use slightly better secret sharing. Let's start with two-source extractors. It's good secret sharing. It has some additional features. Why not? So let's try to encode the secret in ZP. with two vectors such that the inner product over ZP is equal S. So it's good secret sharing. It's also resilient to leakage. Maybe it will help. There is attack, unfortunately. We pick any A, non-trivial A, not equal 0, not equal 1, and we multiply L by A. What we obtain if we try to decode this? Well, if we count the inner product of those two, we will get A times S. And again, we changed S to A times S. So this is not the combination of non-malleable of identity function and constant functions. Thus, this is not non-malleable. But I said that we have to pick A which is non-trivial, so non-zero and not 1. Well, if P is equal to, there is no other A. So maybe it will work if P is equal to. Maybe it will work for a small field. So the same setting, just the field is smaller. And I guess you can guess by this amount of space I left that there is an attack, and you'd be correct. The attack is a bit different. What's the problem with inner product? The problem with inner product is how you calculate it. You take the first coordinate of this vector, you take the first coordinate of this vector, and you multiply them. Now, if the coordinates, if everything is uniform, then multiplication of two bits with probability 3/4 is equal 0. So what we do, we put 1 on the first coordinate of first vector and 1 here. What happens now? If we try to calculate this inner product, then the first coordinate will multiply to 0. When with original coordinate multiplied to 0 with probability 3/4, here the multiplication will be 1. So the original secret and the new secret are different with probability 3/4. And if you remember the second definition said that you cannot flip the secret with probability significantly greater than half. And last time I checked, 3/4 is significantly greater than half, so this is clearly not non-malleable. So we got the problem. We would like to use inner product, but on the large field, the adversary can exploit the non-trivial linear structure. While for a small field, it's a problem of non-uniformness of bits and stuff like that. So we got a problem here. First of all, it's not really a problem of inner product, because if you think of any other extractor, they all have some kind of group structure, linear structure, or something like that. And there is no reason to believe that adversary won't be able to exploit it. So the thing is, we would like to really do something with the field. We would like to combine the advantages of the large field with the advantages of the small field. And here comes our construction. We choose large field F. And this time size really matters because the security parameter will depend on it. We choose any element of that field, C, and take any extractor, where G is any set. It can be a vector space, whatever extractor you choose, just here. Now, this is the large field, and where is the small field? Because I said we want to combine those two. Well, the small field is in here. We encode only 1 bit. So how we encode the bit? The bit is either 0 or 1. So if it's 0, then we choose 2 elements that extract to C. If it's 1, then we choose 2 elements that don't extract to C. There is a high asymmetry here, and it's absolutely crucial. It won't work without this asymmetry. Not only improved, but there is also an attack. There is one side note. The extractor can't be any extractor. It has to be extracted with some additional feature. We call it flexibility. We explain it in the paper. I don't want to cover it here because it's slightly technical. But yeah, we require something more. Fortunately, all extractors we checked were flexible. So inner product is flexible. The extractor, when you multiply stuff over Galois field and then truncate, is flexible. The extractor with these matrices multiplied by vectors is also flexible. And it's all good. We can choose basically any extractor. All we checked were flexible. Now, small remarks. The security parameter depends only on the size of field, and if we go with inner product, so we choose the vector space as a set G, then the parameter, anyway, then the N, the parameter here, plays role only in the leakage feature. It does not depend on security parameter. Okay, so the leakage feature, I mentioned about it a bit earlier in Lizanska and Liu paper. So it's a feature shared by both Lizanska and Liu paper and our paper. The idea is as follows. We encode the bit with two parts. And what would happen now, now the functions f and g would be applied separately to this and separately to this. But let's make it harder. So let's give some adversary some additional information. Let's allow him to leak some additional information. So the adversary can leak adaptively from L and R, and based on the leakage he receives, he can choose the functions f and g. So in a standard model, there was no this and no this. In a leakage model, there is a leakage before choosing the functions f and g. And now some parameters. If the length of L and the length of R will be denoted as n, then total adaptive leakage we can tolerate is half of n, up to half of n. So yeah. Now, yeah, the recent paper. There is a recent paper, Non-malleable codes from additive combinatorics. It's the paper by Divesh Agarwal, Evgeny Dodis, and Shahar Lovet. They show the construction of non-malleable codes for any size message. It's a very cool paper because it uses the additive combinatorics stuff. They use the recently proved theorem, quasi-polynomial Freeman-Rouge conjecture. Well, it's not conjecture anymore, I believe, for half a year. So it's really the latest stuff, latest methods, and really cool paper. Yeah, that's all. Thank you.